When we think about what our universe is made up of, we automatically think of stars, planets, galaxies. But the reality is that that is less than 5% of the mass of the universe. The other 95%? Well, that's one of the biggest questions in science today, and what some of the greatest minds in astrophysics are trying to decipher. The hunt for dark matter has spanned decades, and though we can't see it, smell it, feel it, taste it, or hear it, we can see its gravity impacting other things. So if we only really know 5% of the story, discovering this elusive dark matter would unlock an entirely new understanding of everything and everyone in our known universe. So how close are we to finding dark matter? If you're not really familiar with dark matter, let me get you up to speed on what we know so far.
What we know is it exists.
And that's about it. No, seriously. But there are a few things we are at least confident about.
Dark matter is this really mysterious, strange substance. It's amazing in some sense because it's all around us. So right now, as I'm sitting here, dark matter, a wind of dark matter is going through me. It doesn't interact with me, which at least it doesn't interact with me much. So my body doesn't realize it's there, the Earth doesn't realize it's there.
We are pretty sure it's a new particle. If it were not a new particle, if there's something totally crazy, then science would be revolutionized overnight in a way that has never been in the history of mankind.
And then finally, we know a lot about what dark matter isn't. So there have been lots of different kinds of experiments that have looked and tried to discover what dark matter is and haven't found it yet. And so we've excluded a lot of possibilities.
But why is this missing piece of our universe so important to find and understand?
It could be that someday if we could manipulate this stuff, we could actually use it as a source of energy or something. So, in the far future, there might even be a huge payoff for us if we could manage to do that.
In the late 1900s, when J.J. Thomson discovered the electron in cathode ray tubes, nobody knew what the electron was good for. He just thought this was an interesting thing to study. And now when we think about how we live our lives, we all go around all the time with our heads in our phones, which are packed full of devices that rely on the quantum mechanical properties of the electron. And so, although we haven't found dark matter yet, there is a huge amount of it out there, and understanding its quantum mechanical properties, who knows how it's going to change our lives.
This is a puzzle that is being put forth by the universe to us, and I cannot think of anything else better to do with my time than to try to answer that puzzle.
Even though we haven't seen it yet, there are a few key pieces of evidence we have found so far in the search for dark matter that tells us we're on the right track.
We are certain that dark matter exists because the evidence for additional mass in the galaxy is all over the place in astronomical observations. You can see the gravitational pull on stars and on galaxies, to even a lot more subtle things, like you can see the relativistic effect of invisible clumps of dark matter causing light rays to bend.
Most recently, there have been beautiful observations using optical data and X-ray data, looking at gravitational lensing to infer the distribution of matter in colliding clusters of galaxies.
But by far, the smoking gun for dark matter is the cosmic microwave background. This is the earliest thing that we can see through our telescopes through light.
It's basically a photograph of a moment in history after the Big Bang, when the universe was only 380,000 years old. It also shows temperature data. And when we measure the fluctuations in temperature, the position of the peaks can determine the ingredients of our universe. It shows that less than 5% of the total mass of the universe is made up of what we call normal matter, like visible stars, planets, and galaxies. Then 26.8% of the mass of the universe is dark matter, and the rest is made up of dark energy.
If you ask me what dark matter was, I'd say, I have no idea. If you ask me what dark energy is, you wouldn't be able to show that because it would be, I have no bleep, 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 bleep idea.
Which means we should just leave dark energy for another day. Now, the reason the CMB was so significant in proving dark matter exists is because when we compare theoretical models with these peaks, there's an extremely compelling match, practically ruling out a universe without dark matter.
So basically, putting it all together, dark matter is the simplest explanation we have that explains all of the data that we have from different types of observations.
To match these discoveries and observations, scientists came up with a theory for what dark matter could be: WIMPs.
WIMPs, which stands for Weakly Interacting Massive Particles, but of course the name WIMP is so cute that everybody likes to use it instead, are particles that are heavy, and that's where the massive comes from. And weakly interacting means that they have an interaction strength that's maybe around the electroweak force. WIMPs started being discussed sometime in the 1980s. They've really been dominating the conversation, I would say, until about the last 5 or 10 years. So WIMPs are beautiful because they solve a lot of problems kind of for free. You don't add too much, you just get a lot of explanations for mysteries that we want to know.
If we can find WIMPs, it's possible that that would then mean we've also found dark matter. So scientists began planning and building a lot of different experiments to look for WIMPs, dispersed all around the world.
Experiments look for dark matter in 3 ways. You can make it, break it, or shake it. So the experiments that make it try to produce dark matter particles in ultra-high energy collisions of proton beams at accelerators, like in the Large Hadron Collider. And those experiments look for some evidence that dark matter particles were produced and flew out of the detector.
The Large Hadron Collider is pushing particles together at such high speeds that when they slam into each other, the kinetic energy that breaks off can be frozen into matter to be studied. It's possible that these tests could generate something that matches the properties of dark matter. The second search method is called indirect detection, the break-it method. This is when we observe dark matter in space, and since it's so far away from us, we're only seeing what is produced when dark matter particles are annihilating each other, which would happen if there's a high enough density of them. And finally, the shake-it method is actually called direct detection, because scientists theorize that dark matter may set off extremely sensitive detectors.
I work on the DEEP experiment, and we use a detector which has 3.5 tons of argon and is located a mile underground in Sudbury, Ontario, Canada. And what we're looking for is some evidence that a dark matter particle struck an argon atom, and then that argon atom deposited the energy in the detector, and that produces a flash of light.
It takes months or even years to get the experiments going, and they often run for months or years just collecting the data that they need in order to see if the dark matter is there where they think it might be.
So with all of these different searches and all of these different methods, have we found anything close to WIMPs?
We've been looking for almost 25 years, and we haven't seen it yet.
That means that WIMPs are still allowed to be the answer. On the other hand, when you don't find something for a few years, then you start to think, all right, well, maybe I'd like to look in other places too. And I think what we're seeing now is a push in that direction.
In fact, the search for dark matter is experiencing a major, exciting shift right now for the first time in decades. The search for WIMPs will continue, but scientists are clamoring onto the scene with new ideas for what dark matter could be, bringing the hunt to new corners of the universe.
Once you go beyond the idea of WIMPs and start thinking about other ideas for what dark matter could be, you find actually there's a lot of great possibilities. So there are very light mass particles like sterile neutrinos, which is kind of a cousin of the neutrinos that are part of the Standard Model, or axions. This is kind of a very, very light particle that explains certain mysteries for the strong nuclear force.
One thing I'm actually really excited about is looking for dark matter through new forces. And I think this is an avenue that is a relatively modest mathematical change to the theory that opens up a whole new range of different experimental handles.
You could imagine that it's actually something to do with extra dimensions of space, where at every point in space there's a different direction that we can't see because our eyes don't know how to look in it, but you can actually send energy into it and you can have particles that live in it.
I'm really interested right now in the possibility that dark matter might actually interact with electrons. And so I'm focusing on looking at searches using an alternate signal. And I think that that's kind of a trend for a lot of experimentalists, is that we're thinking about how can our experiments do more? How can we test other possibilities?
These are just a handful of new theories. There are so many more, with great names like fuzzy dark matter. Or what if there was a periodic table of dark matter just like what we have for elements? Testing these new theories can be folded into existing experiments or drive completely new ones.
Other ideas are actually more exotic. You could imagine that you're going to use gravitational waves to discover something about dark matter. Other advances are more in the way that we actually do analysis. So there are things like machine learning that allow us to be very sensitive to tiny and very subtle signals that are buried in complicated backgrounds. The machines can be trained to discover things that your eye wouldn't be able to pick out from a set of data.
So, to recap, we know it exists, we've been searching primarily in 3 different ways for WIMPs, but haven't found them yet. In doing so, we've eliminated a lot of what dark matter is not, which is progress. And we have a bunch of new ideas to explore. So, how close are we to finding dark matter?
If the current round of experiments are going to be able to discover dark matter, right, and there's a good reason to think they might be, I think we would know in a couple of years. On the other hand, if these experiments are not quite what we need, it could take longer than that.
And I'm an optimist. I'll tell you I could find it tomorrow. I might have already found it, and I've got 2 years of data in the can that I haven't looked at yet.
It may be right around the corner. The honest answer is we really have no idea. But it's exciting because we have a fighting chance of being really close.
It is a hugely exciting scientific question, and there are great experiments taking data now and big leaps forward in sensitivity. So I think the chance that we discover dark matter in the next 10 years is good. You know, I'm betting on it.
When the discovery comes, it's going to be like a bolt of lightning and it's going to change everything.
How close are you to following Seeker on Facebook? We don't want to be on the dark about which matters you'd like us to investigate next. Leave a comment below and don't forget to come back here for more cutting-edge science coverage. Thanks for watching.